As you can see, this lecture is not exactly mine. Vasilis used to help me in this module when we did some reshuffle of the roles, and now Vasilis is not any longer a lecturer in this module, but I found some of the materials that he created for me quite useful, so why not to use them. My apology for not using every slide here. This module is evolving a little bit. You can even see the old title and the old symbol of this module. So we will adapt this slide presentation a little bit. But first of all, lecture overview will consist of main theoretical concepts and practical examples. I will limit on the theoretical aspect of this. Some time ago, when this module was specifically 3D graphics without artificial intelligence, basically we had more time to do 3D graphics, and we went sometimes a little bit deeper into some theoretical concepts. Since that time, we introduced AI to the module, which I think is a very interesting addition, and the 3D part moved to more practical than theoretical aspect, which I think, after all, is also quite a positive outcome. All right, so terrain creation. That's basically the idea. This is the real landscape and the real photo of a real landscape. And here is our simulated landscape. So this is basically a mesh, a 3D mesh in this case. You can see these white lines here. These lines visualize normals, okay? I hope you understand. You must remember what a normal is. That's the perpendicular vector to any surface. Normals should be normalized, but it's a detail. I'm not sure if these are here normalized, but you can see that normals have to follow the shape of this landscape. Okay, so on the slopey areas of this terrain, the normals have to be a little bit diagonal, okay? But before we go to 3D terrain, let's have a quick look at how you could do a 2D terrain. And these ideas presented here can be reproduced in 3D graphics as well, because this is basically how to create a tiled-based terrain. We have a set of tiles on a regularly spaced grid. Each grid is in this square. It's a square occupied by a tile. So we have square tiles. We can apply something like a 45-degree view at these tiles, but it's even if we do something like this, it's still a 2D landscape. Sometimes you would prefer to use a hexagonal grid to get a little bit more interesting effects. But now we will concentrate on the very simplest square grid, square tiles that might look like this, right? Of course, in a real game, I would get rid of those bright green lines that you can see here. So this would look a little bit better. These lines are, of course, for us to see where the boundaries of these tiles are. But it still doesn't look very good, does it? We have very clear borderlines between various types of this terrain. And I wanted to present a simple technique which can alleviate this problem. And this can create a terrain that looks much more naturally, like this stripe here in the bottom of the screen. How it can be produced? By creating, well, 16 possible edge transitions and 16 possible corner transitions. You can see the complete set of those transitions here. The edge transitions are the upper row, the corner transitions are the lower row, sorry. Now, it's important that black areas in all these types of grids, of square tiles, maybe more than grid. The black areas are transparent and gray are solid or opaque. Okay. Now we can transform these patterns artistically to create nicely looking transitions. And please remember about transparencies. So black are transparent, gray are solid. If you combine them, okay, thanks to having a transparent part and a non-transparent part, each square in the grid can display just a part of this particular grid, and some kind of a grid which is behind it. Okay, so you can combine these transitions so that we can change from a not very nicely looking terrain like this into something of much better quality here on the right. Okay, so here we have these irregular borderlines between various types of terrain, just by applying two different tiles at one position in reverse order of precedence. This creates something much better. So that's the basic 2D technique of creating tiled landscapes. But please note that as soon as we learn how to apply textures, and particularly multiple textures, so applying two different textures to the same part of the terrain, and these textures can be combined with alpha channels, so transparency. This method can be applied to use to create texturing of a conventional 3D terrain as well. Okay, so that's absolutely applicable for 3D. But time came to talk about 3D terrain. The 3D terrain, there are several different techniques to create 3D terrain, of course, and the one presented here is not the only one. But it has some real advantages. First of all, it's easy to use, quite effective, but it has some shortages, some aspects of the landscape that cannot be efficiently produced with this Heightmap approach. Anyway, it's something recommendable, and that's exactly what we are going to use first of all. So, what is a heightmap? Heightmap is essentially a 2D array of pixels. Even more, a heightmap will be quite often represented by a bitmap image, okay, bitmap image. And now it's a 2D array of pixels, normally in the range 0 to 255. Okay, this means that it's not a colored image. It's usually a black and white image in which we have 256 levels of the color gray. Okay, 256 shades of gray. Now, black pixels are the lowest, light pixels are the highest. Okay, so we just have a map like a conventional physical map showing the height or altitude of the terrain, Okay, and in this case, the 0 value in the pixel, which is normally black, okay, means the lowest position, and all the shades of gray are represented by numbers from 0 to 255 would translate into various height up to the highest white point. Generally, you can use Photoshop, GIMP, or any other tool to create a noisy but smooth image. Okay, noisy because we need to have some diversity in this terrain, but smooth because we want this terrain to look rather, smooth and nice. We translate each point in a grid by a factor of the corresponding pixel in the image. And the result is like this. This is the height map, and this is the resulting terrain. All right, so this method really works. Basically, that's the terrain that I will show you in a moment. The height map, actually, the terrain will be demonstrated in a few minutes. Okay, so as we mentioned, dark is lowland, bright is the highland. Okay, height maps are usually a square bitmap mapping heights into grayscale. Now, how it can be done? It's a grid, okay? It's a network of points. Now, coordinates of these points in the bitmap are translated into x and z coordinates in the real world, in the scene. We would count them from -n to n, so that the point with coordinate 0, 0 are in the middle of the bitmap. And now the height of the gray point between 0 and 256, 55, represents the y coordinate. Now, the problem is that it creates a grid of vertices. All right, we have to apply faces to these vertices. There is one technical problem with that. If we think about 4 neighboring vertices, like this one, 1, 2, 3, 4, okay, or 1, 2, 3, 4. There are 2 different methods shown here to connect these points into corresponding triangular faces. So the same structure of points, of vertices, put into some kind of a height, can represent a ridge like this, or can represent a valley like this, right? So yeah, this is a elementary difficulty with height maps. Fortunately, this dilemma, this double possible representation, it's on a very small scale, because this is only on the directly neighboring vertices. Okay, so bigger, larger forms, larger land masses like mountains will usually be transformed quite well with the height map, but you have to remember that on the very small scale you have something like this. There are several solutions that you could try. One solution is just assume that we would either go like this or like this. Okay, you could also allow your terrain editor to flexibly switch diagonals as you need them, or even it's a compromise. It's a little trade-off, because it can create a height map that doesn't have this double possible interpretation, but we lose a little bit on the resolution of a bitmap. And this is constraining all quads, so all areas of 4 vertices, to be planar, to be flat. Okay, so no such situation like here. They would have to be at the same level, so that we would then create a height map in the form of quads rather than triangles. But the easiest solution is just don't mind, forget about the problem. when you have a particular implementation that either takes this red edge or the green edge, you will, at least from one height map, you will always get the same form of the terrain. And this is actually what we apply in our software in the 3DGL library that you are using in this module. And this library actually provides you an implementation for using height maps and creating terrains based on a height map. Okay, so this is an example height map. Now, for those of you who would like to look into the code creating the height map, this is now, we are now entering something that is not a strictly required part of your knowledge of your lecture outcomes, because this implementation is included in 3DGL, and this is perfectly fine that you just use this representation there. But anyway, there is a few pieces of interesting C++ code, so I will go very quickly through this code, give you some comments. The rest is for you to read, either here from these slides or perhaps even better by starting Visual Studio and looking into the actual code. So first of all, the heights can be represented as a STL vector, okay, and this is in many aspects a better solution than using a conventional C++ array. We have to reserve space for the entire map. We have a nested loop to read the pixel values at the position ij from the image that is, of course you have to download the, load the image first, but then we take pixels from this image and we can push them back into the heights, okay? So this is how you, with a simple function called to pushback, you can just store consecutive pixels in the form of a vector, one-dimensional vector. No, it's one-dimensional array in the form of a vector, never mind. Now, collection of vertices is quite easy. Again, that's a double nested iteration, and this time we have another vector of vertices. Please note that this is a vector collection of OpenGL float values, okay? So we just saw it not as a collection of 3D coordinates, but XYZ, 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 a collection of float values. And for each point on the map, we will send equal to x minus n size divided by 2. So it's the x coordinate translated from the position on the map, remembering that we have remapped these map coordinates so that the 0, 0 coordinates are in the center of the map. So x and z are emitted in this easy way directly from the control variables in the loops, and the y coordinate comes from the height, okay? So from the value originally taken from the height map, okay? The gray point from the height map. And now a little bit of real OpenGL, prepare vertex buffer. Here it is. Okay, that's our code similar to what we analyzed in the lecture about the VBO's vertex buffer objects, and we just create one. And now it's important to notice that we have a grid, okay, a rectangular grid, and the faces that we are going to create are triangular. So each square has to be divided into two faces, T1 and T2, or triangle 1, triangle 2. But also you have to notice that if we store the vertices as we did here in this loop, okay, We will store them by row and column. Okay, so they will be like this. So if this is position xz, this is position x plus 1z, so probably consecutive position in the buffer. But then we have all other vertices and these vertices. So between this vertex and this vertex, there is a considerable distance. Okay, and this is why we want to use indexed VBOs. So that first of all, we can reuse vertices. If you look at any particular vertex, for example, this one, it is used by a triangle in this square, by two triangles in this, another two triangles in this, and one more triangle here. Okay, so it's 4, 5, 6. Each vertex is used by 6 different triangles. So we don't want to store all the triangles in a sequence, mostly because we would have to rewrite the same vertex 6 times. Okay, so it's a huge saving in memory, and also we would have a very complicated stuff to create this kind of a loop. It's just easier to store them those columns, okay, like a rectangular grid, and then just find the values of the indexes. I won't go into pretty much detail about it. It's just for you sufficient to know that we have to create these indices so that to represent the structure of the triangular faces. And that's the corresponding code. So if the current point is zx, okay, please remember that we are working on a one-dimensional array. So the position of in this array is the z coordinate multiplied by the size, so the length of the entire row of pixels plus x. Okay, but then the next row is z incremented by 1, and the next column is x incremented by 1, right? So this is how we create one triangle, and this is how we create another triangle, okay, in the system like this. One important point here to notice is that these indices are not necessarily consecutive vertices in the collection of vertices, okay? Actually, it's quite rare, okay? In two cases they are consecutive, in two other cases no, it's just in one case, okay? Because even if it is these two vertices, they are going the other way around, okay? Counterclockwise. So no, it's just one situation in which we take two consecutive vertices. All right, so this is how we collect indices. There's one more thing. Here we prepare index buffer. One more thing that requires a little bit of maths, and I will not stay on this very long. I'll just explain why we do this, and anyone interested in the topic can analyze this maths or try to find your own solution. Basically, this is about creating normals. You know that normals are absolutely a must in 3D rendering, and the Heightmap does not contain any normals. So what we can do, we can find out the slope between neighboring vertices, all right? And this is exactly how this normal is constructed here. So basically, if we have a node here, a node here, and a node here, then the normal at this position is interpolated between this and this. We just know what kind of a slope we have by comparing the y variable in the current node and all neighboring nodes. All the math is here. It's based on the cross product, and if you remember anything from vector algebra, cross product is the easiest, the fastest way to find a perpendicular vector to some surface. So basically what we do for this point here, we take its 4 neighbors, not all 8 neighbors, just 4 neighbors. This neighbor, this neighbor, this neighbor, sorry, this neighbor, and this neighbor. Out of these 4 neighbors, we construct 2 vectors, one vector and another vector. Okay, these 2 vectors construct or create a 2D surface. Okay, and we can assume that this 2D surface, which is attached to these 4 points here around the central point, has a slope corresponding to what we should expect in the center of the structure. Therefore, if we take these 2 vectors, calculate the cross product of these 2 vectors, we get the perpendicular to this small surface here, and this perpendicular is a very good estimation of the real normal value at this point in this mesh. This method can be replicated in any situation in which you have a 3D mesh, okay, a 3D mesh without normals, okay. So for each point you can find 2 vectors based on neighboring positions, neighboring vertices, find a cross product, or of course normalize this cross product, you get the normal, okay. So that's how it works. Here's the corresponding code, which I will leave to your own analysis, because I already have an impression that I stopped for too long in analyzing this source code. Okay, preparing the normal buffer, that's the usual or standard OpenGL stuff. And this is how you can render the terrain. Okay, enable client state. So this is very conventional rendering of a VBO, of a vertex buffer object. And now this is the final effect. Now I have 2 news for you. Okay, one is bad news, one is good news. Okay, I will start from bad news. Okay, bad news is that Heightmap technique has some limitations. For example, here is a clear limitation of this approach. If you have any kind of overhangs, devil towers, or even caves, you cannot easily build them using a height map. Okay, just think about any point above this rock arc formation. Okay, for any combination of x, z coordinates, we just can provide a single height, right? So we can provide the height of perhaps the top point here or the bottom point here, okay, but not the entire 3D structure. So that's the big limitation of the height map approach. How this can be solved? Several possible. I will stop on this. Several possible solutions for this. One solution is you just create the basic terrain without these special formations, and you add these special formations as additional meshes. So you have to, in this case, you have to combine 3D terrain with additional objects. Another possible approach is to provide a triple height map. Okay, it's maybe not the most efficient method, and it will also allow you to create just a single cave at a given XZ position. You cannot create systems of caves one under the other like you have in Minecraft, for example. But what I mean with this triple height map, there would be one height map with the upper terrain, upper shape of the terrain. The second height map would map the lower part of the terrain, so this one, so 1, 2, And we also need another height map just to represent the ceiling of any kind of a cave. So this would be this surface here. So with a triple height map, you can have 3 different levels. So top level, cave ceiling, cave floor. So you can represent a cave in this way, but as I thought, not multiple caves one on top of the other. For multiple caves like Minecraft, we would probably have to go into some kind of a voxel representation. Actually, Minecraft is a voxel representation because of you have all those cubes, all right? So this creates a really real 3D structure. So to anyone interested in creating complex terrain forms in which you can dig or change the shape of this height map very easily, I would send you to methods, for example, such as marching cubes, for example. Okay, but we will not discuss these methods today. Actually, enough of this theory. Let's have a look at the terrain that I'm giving to you today. So first of all, in the home page, you have the asset store. Okay, this is the asset store for this lecture. Good news is everything is free here. Everything free. And in this asset store, you have projects. Okay, and one of those projects, central today, is called First Terrain. Okay, so if you'd like to create a terrain scene, you should download this First Terrain. It's even better than the first scene that you are already familiar with. I have downloaded this project already, and I have it here, the First Terrain. And what you can find in this project, first of all, models. Okay, in the models we have the height map. Okay, can you see it? That's the height map. So we have 3 hills here because hills are the bright aspects, bright areas. That's a very low resolution, okay? Because that's just an example, and I really hope that when you create your scenes, you will replace this teeny tiny height map with something much more impressive and much better. So that's the height map. So we should expect 3 hills, one of them more like a ridge than a hill, and 2 smaller hills. All right. So that's one asset that I'm giving to you. There's also another one. There is a road structure. You will see in the running project in a moment. I also am giving you a street lamp object. Just a moment. Paint 3D takes a lot of time to display even a simple project. Maybe I should show it here in the box. It's faster. So first terrain. Let's go to 3DGP models. Okay, that's the street lamp for you to use in your landscapes. Now loading Visual Studio. I will run the program first, and this will display a very simple terrain. No textures, because you don't know yet how to get textures. Not very good lighting, so when I'm looking up and down, this light changes. All right, but this is deprecated functionality. You will replace it with your proper shaders, and you should actually improve this lighting, definitely. Okay, so we have a road here, and we have these hills. We also have, sorry, I went up. We also have navigation. So I'm now pressing W, and you can see we are traversing. It's not a very long terrain, so here is the end of the world, but you can see this is the ridge on the left. This is the ridge landform, and on the right we have two smaller hills. The navigation in this program automatically checks the altitude, the shape of the terrain, so I can easily climb on these hills, okay, and see the landscape from here. All right. I'm not sure if it is the most efficient solution, but it's the simple and fast. But the road here is created as another height map, okay? But this one is very long and narrow, and shaped basically like the main height map here. All right, so that's the program that I'm giving to you. Remember that all 3DGL programs can be switched into the full screen mode by pressing F11, or switched off by pressing F4. So time now to look into the source code. Okay, it has these two shaders here, but shaders are currently not in use. You will have to convert your program so that they use shaders. And just let's have a quick look at how we can create this terrain, and also how we can improve the navigation so that we follow the profile of the terrain and we can easily climb the hills. So nothing special here. Please remember that when you switch into the programmable pipeline, you should get rid of the deprecated functions such as all style light setup. And here is how you load the height map. So that's similar to loading a regular object. The difference is that you use load height map function call, and what you load is a bitmap. Okay, in this case, this is the BMP file. 10 is the scale. By changing this to another scale, like say 30, okay, we will create a terrain that is much higher. Okay, these hills should be much steeper now. Okay, so that's what we have when we put 30. So it's basically up to you what kind of a shape you want to get. So these are the same hills, but much higher now. All right, nothing else particularly interesting here in this part of the program. And setting up the camera, what's important are these two lines, but they are written for you, so you don't have to do anything with that. Terrain Y is the function call that takes the interpolated height from the terrain. Oh, I've forgotten to tell you one important thing. We use here a special C3DGL terrain object, which is provided for you in the 3DGL library. So you don't have to do all this coding that I showed you in the lecture part. This was theory behind the practice, all right? In practice, nobody would create terrain out of individual vertices. You have a ready-to-use class of objects that can load the terrain like this, and can also render the terrain in one single call like any other mesh, all right? So this is rendering the terrain. This terrain objects also provide a special function get interpolated height. Get interpolated height provides you with the exact height value for the given x, z coordinates. And this is quite often a question coming back from students, how we can discover our current position within the scene, within the world. And if you remember the lecture about matrices and transformations, our matrix is generally a combination of various rotations and scaling and the translation, the position, XYZ position, to which our camera is moved, if we are talking about matrix view. And the rotations are the 3x3 upper left area of the transformation matrix, whilst the translation is the fourth column, right? So by using the inverse of matrix view, because matrix view is it's the transformation that creates the position of the camera. So every object will be moved away from the camera, okay, to provide the perspective, relative view seen by the camera. To get any point towards the position of the camera, you have to apply the inverse transformation to our current matrix view, but it's that simple as this function call here. All right, so we take the inverse matrix view, and now position 3, 0 of this matrix. Please remember that GLM provides the possibility to read individual items inside the matrix like it was a two-dimensional array. So our inverse matrix view at the position 3, 0 will provide you your current X position in the world. 3, 1 will provide you with the current Y position, which we don't use here. And 3, 2 will provide you with the current Z position in the world. By the way, the position 3, 3, you know what would provide? The W coordinate, okay? So 3, 0 is X, 3, 1 is Y, 3, 2 is Z, 3, 3 is the Y coordinate, and if you don't remember what is the Y coordinate, that's the coordinate that we had to add to a 3D structure to make it 4D structure, okay? And this Y coordinate is just 1, okay? So you should discover that inverse matrix view 3, 3 is the value is 1, okay? But now we just extract X and Z value provided to the get interpolated height function of the map, and this function takes these two floats X and Z and returns the Y value, the height value at this particular position. It also makes a very nice thing. I will not go into details, but this is interpolating between the two neighboring positions. So we will not have a jumpy transition between two neighboring vertices. Vertices can be quite far apart from each other, and we still will have a smooth transition between the two heights. All right, and once we have this terrain Y, the height of the terrain at our current position where the camera is, we will just translate the current matrix view by the translation vector 0 terrain Y 0. So the camera will be specifically moved to the current height of the terrain, but this will produce exactly what we want. So the camera will always be on top of the terrain, but without an additional instruction that I will comment for a moment. If we just do that, imagine in every frame of animation, we would put the camera by the terrain Y, by the current height of the terrain up. Okay, in the next frame, it would again go up and up and up and up. And the result of such a practice must be something like that. Oh, what happens? Ah, negative gravity. I can hardly see. Oh, the land disappeared. Oh, so it was deadly. It wasn't the good solution at all. So for this solution to work, okay, if we put the camera up, we have to get it back down. And this is applied here. And the final instruction in the terrain rendering, we just put it back by the same value, terrain y, okay, 0, negative terrain y, 0. It's going back down, done, okay? And with this additional instruction, the camera will not escape into the skies, but will stay next to the ground, okay, but always on top of this ground. So that's nice. So we can very easily climb the mountains or go down the valleys, right? And before this session is over, I will just show you